Okay, welcome all. Today we will be talking about facility location models, and we will continue our discussion on facility location models. And in today's lecture we will be talking about multi-facility location problems first. We will formulate these problems, consider some aspects of these problems, and for some special cases we will be solving or think about how we can solve these problems. And later on we will consider discrete location problems. So let's get started. Okay, in multi-facility location, different than the single facility location, we are trying to locate a number of new facilities, not only one, but more than one. And we will represent these new facilities that we will locate as x1 through xn. This n will represent the number of new facilities that we want to locate. Similar to single facility location, we have P1 up to PM. These are the existing facilities. So if we consider this figure over here, we assume that in this example there are P1 up to P5 existing facilities, and we know their coordinates. Remember, in single facility location we were also knowing these locations, and this P1 was A1 and B1 x and y coordinates, and P2 was A2 and B2 x and y coordinates. So we know these coordinates. What we want to know is we don't know the locations of these new facilities, which we represent in this example by x1, x2, x3. So we are locating 3 new facilities. And remember, in single facility location we denoted them by x and y because there were only one facility. But now since there are 3, in this example 3 new facilities, I need to put an index for these variables. So this will be x1, y1, the coordinate of the first new facility. x2, y2 will be the coordinate of the second, and x3, y3 will be the coordinate of the third facility. So according to this one, how many decision variables we will have? For each new facility, we have 2 decision variables, x1 and y1, or xi and yi. And if we are locating, let's say, 3 new facilities, in total we will have 6 decision variables. In the case of single facility location, we only had 2, x and y. Okay, so these are the decision variables. There's another difference. Okay, the similarity is this. We still have this weight between the new facility and the existing facility, this W. Okay, Wij. Let's say this one. The weight between the first existing facility and the third new facility. What is it? We will represent it by W13. Initially, we only had these weights with a single index, Wi, because all these weights are with respect to the only single new facility. But since there are now a number of new facilities that we are locating, we need to separate them. Therefore, we are writing them as Wij, and this first one is the first existing facility, and the second one is the third, in this example, the third new facility, W1J. For example, this one over here, the weight between them is W22. For example, this one over here, it will be W, the third new facility, and the second existing facility. So the order is important. In this definition, we are assuming that the first index I represents the existing facilities, and the second index J represents the new facilities. Okay, So this is similar to the single facility location. But the difference from the single facility location is these new facilities that we are going to locate may have interactions between each other. Maybe we will be moving materials in a manufacturing system. These are two machines, and we will be moving materials between these two machines. Then how many trips we are making between these two machines, depending on that number, again we have a weight, and we represent this weight by VJK in order to formulate multi-facility location problems. And it will be the weight between new facility J and new facility K. So for example, this one V13. Okay, but there is actually two things here. Why do we represent it by V13? Maybe it is V31. Okay, since 1 and 3, both of them are the new facilities, then it can be V13 or V31. And actually, yes, we will assume that V13 and V31, they are symmetric. They are equivalent. Therefore, you can write only one of them. You can consider V13 and not consider V31. Similarly here, you can represent it by V12 and the interaction between these two, V23. Okay, so usually we can represent, as I said, because of this reason, we can represent this VJK between two new facilities only for when J less than K. Okay, so V13 and V31, they are the same. So we only use one of them, and we use this one when the first index smaller than the next index. We don't consider the next one, because if we consider both of them at the same time, we will be double counting the travels between these two new facilities. Okay, for example, V23 and V32, they are the same. The interaction between the second and third new facilities. So we will ignore one of them and we ignore this one. We consider this one where the first index is less than the second one. This is just a matter of convention. We decide to do it. If you like, you can think the other way. Nothing will be changed. Okay. So this VJK represent the interaction, or you can assume it as the number of trips per period between the two new facilities. So as I told you, we are assuming that VJK is equal to VKJ between two new facilities. Look, this is not for the new facility and existing facility. This is not valid for Vij, because this I represents in Wij, let's say. This I represents existing facility and this J represents a new facility. So this W for Wij, W12 and W21 is not equal, because this one says that, okay, the first existing facility, the interaction between the first existing facility and second new facility, but this one, it is the second existing facility and first new facility. So it is totally something different. Okay, so this is only for VJK. Then, similar to the single facility location problem, let's write our objective. If we want to use mini-sum objective, okay, mini-sum, we want to minimize the sum of the distances between the existing facilities and the new facilities plus the new facilities within each other. Okay, we need to consider that as well. Then we can write our objective function like this. Since we are locating n new facilities, now my objective, I am representing it as a function of these n new facilities. So don't be confused. This is our objective function that we want to minimize. And this here, this thing inside the function just represents or tells us that these are our decision variables. And the first part over here is the total cost or total distance between two new facilities. How do I understand it? Because of this one. This representation over here, it is the distance between two new facilities. So let's say that this is new facility 1 and let's say this is new facility 4 if we are locating more than 4 new facilities. Then the total distance that we cover between these two will be equal to the distance between them, which I represent by x1, x4, and this needs to be multiplied by the number of trips that I am making between these new facilities. So it will be V14. Okay, so this will be the distance between these two new facilities, but I need to take the sum of this over all new facilities. But here you see in this sum statement I have written something interesting, saying that 1 less than or equal to j, less than k, less than or equal to n. Actually you should read it like this. It is double summation, okay, it's j from 1 to n, and also here k from 1 to n. If I write this double summation in this way, so I need to write, look, what values? I need to write v12 times d x1 x2 plus then at a later time v21 times d x2 x1. Okay, so when you compare these two things, v12 we said that it is equal to v21. And the distance between 1 and 2 and 2 and 1, we assume that it's also the same. Then these two terms are actually the same. And we are double counting it. So we need to eliminate this double counting. And in order to eliminate it, we don't write one of them. And the way to represent it mathematically is this one. We are saying that, okay, we are taking this summation for all j and k. But j and k such that j is less than k. Only for these ones we are taking the summation. Okay, so this statement over here is a double summation of j and k, where we are using the terms only when j is less than k. And okay, we said that this d inside this sum term is the distance. And how do we find the distance between these new facilities? That's one thing. And you can use actually all distance metrics that we learned until now. It can be rectilinear. It can be Euclidean. It can be squared Euclidean. It can be Chebyshev. Or it can be the actual distance. Any one of them. Okay? So whatever distance you are going to use in your model, we represent it by this d. And in the second part of this summation, of course, we need to add the total distance that we need to cover between the existing facilities, this pi, and the new facilities. So if this is existing facility 2 and this is new facility, let's say 3, so the total number of trips that I need to make between these two is equal to the distance between them. Again, this can be rectilinear, Euclidean, whatever, multiplied by the number of trips. Okay, so this objective function simply calculates the total distance, and therefore it's a mini-sum objective, as I indicated here. Of course, in some cases, when there are some existing facilities, and we want to locate some new facilities, some of the weights can be 0. What do I mean? For example, these two existing facilities may not have any interaction. So if, let's say, this is new facility 1 and new facility 3, we may have V13, which is equal to V31, and these can be 0, no interaction. And if that is the case, when we write 0 here, this term just disappears for that pair of new facilities. Same thing applies to these existing facilities. If for some new facility and existing facility, they don't have any interaction, then this weight for them will be 0, and in that case that distance will not be included in this calculation. So we can just simplify this calculation by considering only the positive weights, so that we can define just two sets. The first set represents the new facilities, pair of new facilities. So this is called a pair, okay, JK, pair of new facilities for which their weight is positive. And this set, it is another set, it represents a pair of new and existing facilities for which their weight is greater than 0. Of course, the weight can never be less than 0. It can be 0 or greater than 0. And now in these two sets, we are just concentrating on the sets, on the pairs where the weights are strictly positive. And if we consider this, we can write this objective function in this way. Actually, it is the same objective function. Just pay attention to this sum term over here. Here we said that we are summing up from 1 up to n. Here we are just saying that the pair of j and k should be in the set I1. And I1 is the pair of new facilities for which the weight is greater than 0. So let's assume that these are second and third new facilities, and their weight is equal to, let's say, 7. So we need to include this in this summation. But V13 is 0, as we said before, so it shouldn't be in this calculation. There's no meaning to include it because its weight is 0. Same applies for the second term over here. Okay? So this is just a simplified version of this objective function. Okay, now let's consider the rectilinear case for this multifacility location, and let's write the objective function for the rectilinear case and try to see what kind of a model we are dealing with. Okay, for this let me write, first of all, if this is a rectilinear problem, then how can I represent the distance between two new facilities? Let's say xj and xk, these are two new facilities. Okay, so let me write their coordinates here. This one will have this xj and yj coordinates. Remember, I am representing the facilities with this x with over and under bar so that you do not confuse it with the x coordinate of it. This xj is the x coordinate, whereas this representation with an over and under bar represents the facility itself. Okay, so this is, let me write more specifically, xj has this coordinate and xk has coordinates xk and yk. Okay, and the distance, the rectilinear distance between them actually is this distance. So how do I represent it? It is the absolute value xj minus xk plus yj minus yk. On the other hand, the distance between an existing facility, let's say xj, and the new facility pi can be written similarly as xj minus ai. Remember, ai is the x coordinate of the existing facility. Let me sketch it here. So let's assume that this is pi and it has coordinates ai and bi. And the rectilinear distance between this facility and this facility we can represent like this, and it will be xj minus ai plus yj minus bi. And having these, how can we write our objective function? Remember, we represent the objective function with f, x1 up to xn new facilities, I am assuming. So we are taking the summation over all pair of new facilities which have a positive weight. So it will be Vjk multiplied by xj minus xk plus, this is the x coordinate. Okay, if you like, we can write it in this way. So in parentheses, I can add yj minus yk, and then plus, for the second one, again it will be the pair of new and existing facilities, so j and I, which I represented with this set I2, okay, and it will be wji for positive w, xj minus ai plus yj minus bi in absolute values. This is the rectilinear objective function. And what you can do is you can simply open up these parentheses by multiplying them with vjk and wji here, and then combine the x variables. Look, this x1, combine it with this, and the y1, combine it with this, and at the end we will see that this minimization of this our objective function f can be divided into two parts. The first one will be, I'm going to represent it by f1, which is the x coordinate. Minimize, let me write f1. It will only include these variables x1 up to xn. Okay, and the second one will be the minimization of f2, in which I will solve for the y coordinates. This is the same thing that we did for single facility location. We solved the problems for f1 and f2 separately. I mean x coordinate and y coordinate separately. And here we do the same thing. We can solve the problem separately. So this means that we can solve for f1 and f2 separately. And it means that just divide this problem into two parts, into two optimization models. The first optimization model will include only x variables. The second optimization model will include only y variables. Okay, and then you can solve for it. But for multi-facility location, we don't have that simple procedure that we had for the single facility location problem. But in this course, what we will do is we will formulate that problem and linearize that problem, and we will obtain at the end a mixed integer programming formulation. Actually, it will not be integer, it will be a linear programming formulation, and you can use a solver like Cplex or Excel solver to solve that problem. So let's see how we can represent or formulate this problem, f1 and f2. Okay, so I'm writing the problem for only the x coordinate. The y coordinate is exactly the same, x coordinate problem. So it will be minimize f1, which will include x1 up to xn, assuming that I am locating n new facilities. So my objective or my formulation will be this: minimize, again I am writing the positive set pair of new facilities, so it will be Vjk multiplied by xj minus xk, no y's, plus it will be ji in the second set I2, and it will be wji multiplied by xj minus ai. Okay, now maybe it will be better to write an example over here and write these objective function for that example. Let's assume that we have 1, 2, 3, 4, 5 existing facilities. I am just making up this question, the coordinates of the first facility. I'm not writing the coordinates on the coordinate system. I'm just representing it, 2, 3. The second one, let's say it is 10 and 7. Let's say P3 is here with 1 and 4. P4, 5 and 5. And P5, let's say 7 and 12. And we are going to locate two new facilities, and we don't know their locations. Let's assume that represent one here as the x1, and it has this coordinate, x1, y1, okay, and the second one x2, second new facility, which has a coordinate of x2, y2. Now, as a problem data, I need more information. For example, I need to know the weights between the new facility and the existing facilities. So on these arcs, I'm going to write it. Between this x1 and p1, let me include a third new facility because maybe it will be easier to represent one situation. So let's say that this is the third existing facility with this coordinate. Okay. Now I'm going to write here V13 is equal to V12 equal to 0. So between the first and third new facilities and first and second new facilities, there is no interaction. But V23, let's say it is 4. So what does it mean? There is an interaction between 2 and 3, but no interactions between the other existing and other new facilities. Okay. Then, with respect to, let's say, between the first existing facility and first new facility, V11, let me delete this comma over here. Yeah, V11, the interaction is equal to, let's say, 2 units. Then V12, it is 5 units. V13 is 0. There is no interaction between the first existing facility and third new facility. So I need to write these W values for all pair of existing and new facilities. So I should write V21, and I will say that it will be equal to this one, and it is 0, and V23 is 4. And then the third existing facility, V33 is equal to 0, but V31 is equal to 4, V32 is equal to 10. Then V41, the fourth existing facility and first new facility is equal to 0, V42 is equal to 1, V43 is equal to 7. This is problem data. It's given to you. Okay. And for the last one, this W51 equals to W53 is 0, and W52 is equal to, let's say, 5. Okay. Then when we have this, how can we write this objective function? So we want to minimize this first part over here. The distance between the new facilities, and if you see, V13 is 0 and V12 is 0. So we need to write this only for V23. And what will be? It will be just 4 times then x2 minus x3. Okay? I don't need to write between 1 and 3 and 1 and 2 because their weights are 0. Okay, this is only single term for this first part. For the second part, okay, I am going to write only the ones which are positive. Similar, okay, W11 is positive, so it will be 2 times, okay, x1 minus a1 plus 1, 2 is 5, so it will be 5 times. Remember, the first one is the existing facility, the second one is the new facility. So you need to pay attention to this one while writing these indices, because here if you write, for example, x1 minus a2, it will be wrong, because remember, this a2 represents the coordinate of the second existing facility, but this weight is actually the coordinate of the weight between the first existing facility and second new facility. So the correct way to write this one will be x2 minus a1. Okay, x1 minus a2 and x2 minus a1 are completely different. They are not the same. Okay, so I don't need to write this. It is 0. I don't need to write this. I am going to write this one. So it will be 4 times x3 minus a2. Then I am writing this one. It will be 4 times x1 minus a3. And this one, it will be plus 10 times x2 minus a3 plus, I'm writing this, 1 times x2 minus a4 plus this one, 7 x3 minus a4, and this last one plus, let me write it here, 5 times x2 minus a5. Okay, so what I am trying to do is I am trying to solve this model. And it is not linear because we have absolute values. It means that we need to linearize it in order that to be a linear programming formulation. There are different ways of linearization. Okay, I'm going to use one way of it, in which I'm going to represent each absolute value as a max term. So what does it mean? If you have, let's say, such an absolute value, xj minus ai, then it is equivalent to the maximum of xj minus ai and minus xj plus ai. So this is positive, this is negative of the same thing. Okay, then the problem returns to a min-max formulation. And for min-max, the standard way of linearization is setting this max a variable z and saying that this z is greater than or equal to each and every term of the max. Okay, so for this first term, I need to represent it as max. The second one separately, third one separately. So let me do that intermediate step here. Actually, if you remember our discussion on this linearization from the optimization course, you should be able to directly convert this model to LP. So what do we have? Minimize 4 times, so 4 is outside, maximum of x2 minus x3 minus x2 plus x3. Then 2 times maximum, okay, x1 minus a1 minus x1 plus a1. So this is the second term. And you need to continue to convert all of them up to the last one. Let me write the last one here. 5 times maximum, okay, x2 minus a5 minus x2 plus a5. Now this is a min-max problem, but we have not just a single max, but the summation of these maxes. But the linearization doesn't change with this one. What do? For each max over here, I need to represent it with a different variable. So you cannot just say, okay, this is Z, this is also Z, this is also Z. No, they are different variables. In order to make them different, we include an index here and say that the first one is Z1, the second one is Z2, the third one is Z3. And here, if you see, I have 1, 2, 3, 4, 5, 6, 7, 8, and 9 absolute values. It means there are 9 max. So this last one will be Z9. Okay, so when we do it, what do we have? Let me try to finish it here. It will be minimize, don't forget this multiplier here, 4 times Z1 plus 2 times Z2 plus this one 5 times Z3, then this one 4 times Z4, and it goes up to the last one, which is 5 times Z9. But now I need to write constraints for this one. And what will be those constraints? Actually, for this Z, the first one, Z1 should be greater than or equal to this one, and it should be greater than or equal to the other one. So let me write Z1 must be greater than or equal to x2 minus x3. This is one constraint. And Z1 must be greater than or equal to minus x2 plus x3. These are the two constraints related to Z1. What about Z2? Again, I need to write its constraints. Z2 should be greater than or equal to x1 minus a1 from here. And Z2 should be greater than or equal to minus x1 plus a1, the second one here. And you need to write this for all of them. I am writing it for the last one. Z9 is greater than or equal to x2 minus a5, and Z9 should be greater than or equal to minus x2 plus a5. Now, this final formulation that we obtained here, it is a linear programming formulation. We have a linear objective, we have linear constraints. Our variables in this model are xj for the x coordinates of the new facilities, and also z's, z1, z2 up to z9, which we used for linearization. And this one is only the problem for the x coordinate. Then you need to write another problem for the y coordinate, but that problem will be very similar. I mean, the steps of finding that model will be identical. You will again first write this in absolute value, then linearize it to obtain this such a model. And then when you solve this one and the other one, you will be finding the x coordinates of the new 3 facilities in this example. And then with the other model, you will be finding the y coordinates of the new facility. So we considered the rectilinear distance multifacility mini-sum problem. We formulated it and we linearized it to come up with final linear programming formulation. We can do the same thing for mini-sum problem, multifacility mini-sum location problem with the squared Euclidean distance. Okay, remember this squared Euclidean, it means the straight line distance but squared. And in some cases, this squared Euclidean has meaning, for example, especially in wireless communication, since the strength of the signal reduces usually by the square of the distance. In order to minimize the distance, I mean the distance is squared to show the importance of that distance. Okay, so in such a case, our objective function again for locating n new facilities, we can write again the interaction between the new facilities multiplied by the distance. And as you can see, this distance now is not rectilinear, but it is the Euclidean. But remember, in Euclidean, we should have a square root here. But since this is squared Euclidean, that square just cancels this square root. So we have this formula. Okay, so this first part is the interaction between the new facilities, xj, xk, yj, yk. And the second part is the interaction between an existing facility with a new facility. And again, the distance is squared distance. So if you look at this carefully, you see that it is the summation of two convex functions. In optimization, convex functions are important because when you want to minimize a convex function, if you find a local optima, it means that it's global optima. Therefore, convex functions are important, and this function is a convex function. Okay, this objective function is convex. And in order to find, but it is not linear. Look, we are taking the square of variables. It is not linear. So we cannot use linear programming techniques to solve this problem. But we can use calculus to solve this optimization problem. From calculus, we know that if we take the derivative of this function with respect to our decision variables x and y and set it to be equal to 0, then we can find the values of the decision variables. So with an example, let's try to solve, let's try to understand it better. So let's consider this problem. There are 1 up to 4 existing facilities, and we want to locate 2 new facilities. The coordinates of the existing facilities are given, and also the weights of between the existing facilities and the new facilities, and also the weight, this is V, between the new facilities is also given to us. And the distance here is the squared Euclidean. The question is, find the coordinates x1, y1 and x2, y2 of the 2 new facilities. The first thing, in order to deal with such a problem, is to write the objective function that we want to minimize. So again, I can represent it with f, and since I'm representing just 2 decision variables, I mean 2 existing facilities, those will be x1 and x2. By the way, there's an important property here similar to the rectilinear case. Actually, our objective function here, we can also separate it. It means that we can deal with x1 and x2 variables separately. Okay, so therefore I am writing this in terms of decision variables, not the facilities but decision variables. So I am going to first solve the problem for x coordinate, and then I will do the same thing for the y coordinate. Okay, what is my objective function? Remember, I need to consider the interaction between the new facilities. So the interaction between them, v12 multiplied by x1 minus x2 square. This is the squared Euclidean distance between the x coordinates. Then I'm not writing the y coordinates, only x. Okay, then I need to write the interaction between the existing facilities and new facilities. So it will be 10 times, okay, x1 minus the x coordinate of the first facility is 0 square, plus between 1 and 2 it will be, the weight is 6, and it will be x1 minus 15. Sorry, just a minute. So this v12 here, remember again it is I and j, so it is the weight between the first existing facility and second new facility. So I need to write here sorry, that one was correct. The second one will be 6 times x2 minus 15 square, right? And this one, it will be 2 times, okay, x2 minus 15 square again, 15 square, is it? Yeah, this is first existing facility, sorry. This is x2 minus 0 square, and this one is 2 times x2 minus 15 square, and then this one, it will be, by the way, these weights are given. I think there is this problem with this example. Let me correct it, because according to our representation, remember, it is Wij. This J should be the second, new facilities, and I should be the new facilities. But look, it is written 3 here. What does 3 mean? It is the third new facility, but there is no third facility. So I'm just going to change this example. So this is actually V21, which is 6, okay? And this is W32, which is 16. And this is W42, which is 8. Okay, now accordingly, let's formulate this one. So this first part, nothing changed. The second one, it is 10 times x1 minus 0. It is correct. The next one, let me correct the others. The next one, it is 6 times, then first new facility x1 minus second existing facility 15 square, plus this one 2 times second new facility minus second existing facility, plus this is 16 times second new facility minus third existing facility, all x coordinates, and this one 8 times x2 second existing facility minus fourth new facility, which is 40 square. Okay, so this is the objective function with respect to x coordinate, only x coordinate. Okay, then we can also write for the y coordinates. Okay, so now we have the problem, or we have this function that we want to minimize, which includes only x coordinates as variables. It means that there are only 2 variables, x1 and x2. And in order to optimize this, in order to find the best values of x1 and x2, since it is a convex function, what we can do is we can take the derivative of this function with respect to the first decision variable, which is x1. Okay, so let's take the derivative of the function with respect to x1, the first one. Okay, how do we take? 12 times 2, it will be 24, x1 minus x2. I am taking the derivative with respect to x1, okay? The second one will be 10 times x1, and the third one will be 12 times x1 minus 15. And what I want to do is I want to make it equal to 0. And from this one, we can rearrange these. So 24x1 plus 10x1 plus 12x1, it will be 56x1 minus 24x2 equal to 80. Okay, yeah, this one, it will be 20x1. Yes. Okay, so, but this is 56x1 minus 24x2 equals to 80. And what you can do is you can divide this everything by 8, because they are multiples of 8, so that you will have 7x1 minus 3x2 equals to 22.5. Sorry, this is 180. It is not 80. It is 180. Okay, and 22.5. But can we find x1 and x2 values from here? Actually, no, because we have only one equation and two variables. So, but what we can do is we can take the derivative of this with respect to x2 also. So, in calculus, when you have multivariate functions, I mean functions with more than one variables, we simply take the derivative with respect to each other. Now let's take the derivative of this one with respect to x2. Okay, now it will be 24 x1 minus x2, but when you take the derivative of x2, which is inside the parentheses, you will have a minus 1 coming out of there. And then the second one, since there is no x2 here, it will be 0. The third one, there is no x2, it will be 0, the derivative. And we will have the derivative from here, it will be 4 times x2 minus 15. And the next one will be from this last term, 32 x2 minus 25. And from this last one, okay, in the next line, it will be plus 16 x2 minus 40. Okay, and then we can rearrange everything, and what we obtain is, okay, we first need to make it equal to 0, and we will obtain minus 24 x1 plus 76 x2 equals to 1500. This is what you will get. And then if you divide everything by 4 here, you will get a better version of this one. So what do we have now? We have 7x1 minus 3x2 equals 22.5 from the first derivative. And from the second one, we have minus 6x1 plus 19x2 equals 375. So you need to solve these two equations to find the values of x1 and x2, and from here I don't go into the details how you solve it. x1 star you can find it as 13.5 and x2 star as 24. So remember, what are these values? x1 star is the x coordinate of the first new facility, and x2 star is the x coordinate of the second new facility. So we need to repeat the same procedure for the y coordinates also. Let me write the function for the y coordinates of the two facilities. So it will be 12 times y1 minus y2 square. Okay, again the weight multiplied by the difference between the y coordinates, I mean the distance between the y coordinates of the two facilities, and it is squared Euclidean distance, plus 10 times y1 minus 10 square. Again, I'm using all y coordinates and the weights corresponding to these new and existing facilities, plus 2 times y2 minus 0 square, so plus 16 times y2 minus 30 square, and 8 times y2 minus 15 square. So this is our objective function that we want to minimize. And again, in order to find the optimal values, we will take the derivative of this function with respect to y1 and make it equal to 0. Again, please do it by yourself. And if you do so, you will obtain this equation at the end, which will be equal to 25. And if you do the same thing for by taking the derivative with respect to y2 and making it equal to 0, you will obtain minus 6y1 plus 19y2 equals to 300. And if you solve these two equations together to find the values of y1 and y2, you can find that y1 star is equal to 11.96 and y2 star equals to 19.57. So these are the y coordinates of the new facilities. So if I summarize the solution here, the coordinates of the first facility is the x coordinate that I have found from here and the y coordinate that I found by solving the second set of equations, and the coordinates of the second new facility will be 24 and 19.57. So by this procedure we can identify the optimal coordinates of the two facilities when it is squared Euclidean. Remember, if we want to locate 3 or more new facilities, so we will have their x coordinates as x1, x2 up to, let's say, n. If you are locating n new facilities, it will go up to xn. So when you write the objective function for this problem, this example, then it will include n variables, and in order to find their optimal values, you need to take the derivative of this one with respect to x1, with respect to x2, and with respect to xn, and then you will obtain n equations with n unknowns, and you need to solve it to identify the x coordinates. And similarly, you will repeat the same procedure for the y coordinates as well. Of course, solving this equation system becomes harder as the number of new facilities increases, but it's doable. You can still solve it. Okay, so this is how we locate new facilities, multiple facilities using the squared Euclidean distance.